Welcome everybody. This is part one of our two-part session today, Fundamentals of Force Calibration. Some pictures there. We just went through May the 4th be with you. So that's one. We have our, for those that may have watched G.I. Joes, we have our celebrity endorsement in Sergeant Slaughter, the wrestler from the 80s. And the picture in the middle is a proving ring that is the furthest distance from Morehouse Instrument Company. It's the furthest distance one we've ever sold, meaning that it is isolating Earth's orbit somewhere on the International Space Station. They use this analog device for their ARED, Advanced Resistance Exercise device, so the astronauts that go into space can tune in to say bench 50 kilograms, squat 100 kilograms, do this, and the life science people then monitor the muscle mass, skeletal loss, and everything else. So they have this advanced machine. We obviously this does not come back for recalibration. That's why it's on the International Space Station, because proving rings have a track record of being very stable for very long. It would be fairly expensive to bring it back and calibrate it. Some basics. This workshop is about making force calibration clearer, easier, and more useful to you. If you stay present, you will learn more. That's how it is. If you want to learn more about force, try to stay present. Enter the discussions enthusiastically. That's that chat window over there. That's the questions that you have in your GoToMeeting window. And then say what you think, right? If you have comments as well, that chat window is great to have comments. My name is Henry Zumbra. I'm the president of Morehouse Instrument Company. My contact information is here, hzumbra@MHForce. You can reach me on LinkedIn if you're not connected to me. Now's a good time when we're going over just the basics of the course to go onto LinkedIn and say, hey, let me follow Morehouse, let me follow Henry. If you want to ask me questions, LinkedIn is my preferred contact method. I keep them organized. Email's fine as well. I do not mind that. It seems LinkedIn, we can have that kind of messenger chat going, kind of like a text message. That seems to work for a lot of people when they have comments or questions. So what we're going to cover today is basically the importance of calibration devices and the way that are being used to reduce measurement errors and lower uncertainty. And then we're going to have short breaks and a longer break for the afternoon sessions. What we're hoping you walk away with, a little bit about Morehouse and why and how force force has been around since the start. If you believe in the Big Bang Theory, something blew up or exploded or caused whatever, and things were propelled. Objects were propelled, including Earth and all the other stuff before it formed at a ridiculous rate that it accelerated. And that gets the basic definition of forces, mass times acceleration. Though, why does the equipment exist? Knowledge about force calibration equipment that you may not know. Maybe you're looking to set up a lab. Maybe you're looking to buy load cells. If you make the wrong investment now, it's going to be chaotic for your technicians in the future to live with bad equipment. So we're hoping to steer that conversation to, hey, if I need to upgrade equipment, I need to do these calibrations. This is what I need. So that's a huge takeaway, that those tools and techniques to better your measurements, including the equipment purchases. Knowledge on E74, this is scaled down to a brief discussion. We do have webinars, we have blogs, we have a lot of stuff on E74 if you want to follow it. And then, hey, what are these potential measurement errors? I'm making a measurement today, or my techs are making measurements in the company, and how do we know they're right? Like, do we just assume we can, go out to a hardware store or buy threaded adapters, pull on something and call it good? So we'll cover a lot of that and how to make your measurements better, some tips. Why we exist overall is in the late 19th and 20th century, boilers and steam engines were exploded. 1920s, the problem was getting worse. When a boiler blew up, the material was thrown all over like a huge bomb and resulted in casualties and everything else. Ships, plates were a major concern. Plates were riveted together and different materials could expand and contract at different rates, which would pop the rivets. In fact, it was even speculated. I think everybody on here probably knows the story of Titanic. James Cameron made a great movie about it if you haven't seen it. The Titanic ship, famous ship, that unsinkable ship that hit the iceberg. Well, there's even rumors, and this has some papers on it, that that ship, there was a fire on board the ship before it hit the iceberg, which may have weakening the ship to a point where, hey, we've weakened this material. We've probably popped some rivets because of the expansion of this. And I'm not saying the ship wouldn't have sank, but it's a really good read by NIST that that fire may have ultimately contributed to the Titanic sinking. Maybe if the fire doesn't happen, that it hits the iceberg and it sinks slowly and not as many people die. I don't know, but the reason all of this is happening is because the material was not controlled and testing methods were not good enough. So this resulted in, look, there's great companies out there. Tinius Olson's one of those that's into testing. They built these machines that could test the material. Though what would test the machine? So why we specifically exist and why we started force measurements is because of it's the hardness of material that drives everything that is built. And in order to determine the strength of material, they needed to develop the test protocols to prove the material was strong enough to withstand the forces exerted upon it. So this is, some may have heard of a Burnell test. This is when they use something called a Burnell tester. The Burnell tester used a 10-millimeter ball and a hydraulic cylinder to push that ball against the material. The indentation of the 10-millimeter ball was measured to determine the hardness. The main problem was hydraulic cylinder used to generate forces was described as inaccurate at best. Thus, the Bureau of Standards back in the time, which is currently people know as NIST, but it was the National Bureau of Standards. Morehouse got involved through some relative relation, and Mr. Morehouse working with Mr. Petrenko from NIST, back and forth, we were contracted to start, refine, and develop the proving ring. This happened in May of 1925. So the proving ring has turned 100 this year as of May. So, and that proving ring was designed specifically to calibrate Burnell hardness testers, which would help standardize the applied force and provide a more accurate measure for testing the strength of material. Now, this picture shows one of our earlier proving rings. Serial number 1, serial number 2, and all these were more prototypes in 1925. This one actually went to a customer. It was a Burnell proving ring, serial number 14, and was calibrated that by the U.S. Bureau of Standards. There's their test number 47197, May 24th of 1926. So I chose this proving ring because we had records of its service, and it was in service from 1926 to 1984 was the last time we saw it. Doesn't mean someone might not have went somewhere else to have a calibration, though this ring was in service for 58 years. And you can see the certificate from the 1926 to the certificate of 1984 there. And if you start plotting it and looking at the divisions and measurements, was fairly stable for what it was. What we do, that proving ring led to all kinds of other devices, instrumentation, load cells, and everything else. It led to manufacturing of dead weight machines. It also led to us to have the ability to make our own primary standards to calibrate your instrumentation. And we calibrate force using with very low uncertainties. That's where we come into play. We want to be well, we are a primary standards lab, and when we do not have primary standards, we go directly to NIST for our secondary standard comparisons, our load cells. So we try to keep our uncertainties as low as possible, so that the equipment that you send in, what you have to absorb that uncertainty as part of measurement traceability, the documented unbroken chain of calibrations, each contributing to measurement uncertainty. And I'll go over that. But to say, the easiest thing to say for me is we help labs make better measurements, which then makes the world a safer place, which brings us to our purpose of why we are here and why we're doing this free webinar tutorial, is that we create a safer world by helping companies improve their force and torque measurements. Now, I said some things about us, and I'm going to go by this pretty quickly. We have primary standards to 120,000 pounds, over 500 kilonewtons, other force calibrations up to 2.25 million pounds. That is 10 meganewtons, known to be within 0.01%, 100 parts per million, and our primary standards are known to be within 20, generally known to be within 20 parts per million. We also have the second most accurate torque machine in the world that goes to 2 kilonewton meters, and that is known to 25 parts per million. PTB, the German NMI, has the world's best, so we cannot claim we have that, but we have the second. We'll be number 2 in this scenario. So you have a questions box and you have a chat window. So please put any questions you have in those windows. Some questions that I commonly get are common error sources, which we'll cover. How do I calculate measurement uncertainty? We have a tool for that. How do I know if my device is in tolerance? What are traceable measurements? Proving ring versus load cell, which is better? What adapter do I need? How do I keep my technicians? And then a lot of times people come, hey, I just want to learn as much as possible, and that's fine. So those are just some examples. If you have them, put them in the window. By the end of this course, objectives: identify various types of force equipment, identify potential force measurement errors, implement and apply techniques discussed in this session, and use the appropriate force to make statements of conformity. That's what it's all about, right? Low uncertainties, so we can say customers send stuff to us, or we have equipment we need to use, and we want to say it's good. And I want to know it's good for another year. I want to know it's good for 2 years. Well, how do I know that? So that all relates to measurement uncertainty. The lower that is, the more of a chance you as a lab, by buying the better equipment, applying the better processes and everything else, the more of a chance you have to say your customers or your internal equipment is good. And if you have that confidence that it's good, then you can calibrate other equipment and know that what the measurements you're getting are good. So what is force? It is a derived unit. This is a poster from this with a base units of mass, time, and length. It's shown in this illustration. There are 7 SI base units, and force is the derived unit right here. Not going to spend too much time on all of this piece, because you can go back and you can look at it. But yeah, generally, if we're looking at this diagram, we're talking about the Newton and not the Fig Newton, though it is a good cookie. And my jokes do get worse the longer this course goes, so I apologize. So mass times acceleration, and the CIPM and the BIPM defines the official definition of the Newton as the force required to accelerate 1 kilogram to 1 meter per second in a vacuum. Why is this important? Why do we care? Why are we here? There's a lot of things why force measurement's important. When you're on that airplane, I think most people have traveled, you want to know that you're going to take off and you're going to land. If the center of balance is off, not a good thing. If the material used to make the engine are not proper, they don't have the proper tensile strength, not a good thing. How about a bridge? This is a bridge collapse that happened in Florida. It's just an absolute silliness that killed 7 people that should have never happened because of bad engineering and bad force measurement. Though, yeah, I want to walk over a bridge, or I want to drive over a bridge or drive under a bridge. I don't want it to collapse on us, right? I don't want it to collapse on any of you. There's another bridge collapse caused by problems. Here's a condo collapse. This happened a few years ago in Miami. So what happens if we do not properly perform force measurements? The condo collapse here, this is kind of a fun story in some cases if you read all the documentation and about the residents, and I'll recap it as much as possible. Though, so we have this condo. Residents all say, let's upgrade our pool area that's at the top of the condo. And when they updated that pool area, they also put in these larger slabs and everything else. Well, the building was degrading anyway. And what ended up happening is the punching shear, which is a failure mechanism in the structural members like slabs and the foundation by shear under the action of concentrated load. What the action of concentrated load is on a smaller area in the structure members. In most cases, this reaction is one from the column acting against the slab. Eventually, the slab will fail. So what happened is they redesigned the top. They had some problems with some leaks and everything that was weakening the cement. NIST has National Institute of Standards Technology has more information on this, but they redesigned the top. They wanted a nicer pool area. They put heavier. They made the load-bearing portion of that top. Uh, they exceeded that because they used heavier concrete slabs than it was designed for. Engineer didn't come and refigure all of this, so they put their nice pool up, and sometime later, it all collapses at like 2 o'clock at night, and several people are killed. And it's because people didn't do the analysis right. What else could happen with improper force measurement? Incorrect concrete strength measurement, incorrect steel strength measurement, cables not checked properly for pre-stress or post-tension. You have the picture here, something unstressed beam, and then you have load and deflections, tendon stress, pre-stress forces. If the forces are pushing in, that deflection goes up. If they're pushing the other way, it can go down. So, total deflection there. What we want to talk about is that almost every material item is tested. If you're sitting in a chair, likely somewhere along the way that material is tested. You're using a keyboard, the keys are tested. You're wearing something, your clothes, your fabrics, they're tested. Manufacturers require to do sample testing on the products they manufacture. That keeps us safe, right? You don't want bad lots. We don't want bad material. And these products vary from things that are silly, like, uh, your toilet paper roll, to wood that's used, and things that aren't so silly, to wood that's used to build your house. I mean, when you're there with paper towels, and why does it matter that the paper towels are tested? I don't know. I don't have an answer for that. I don't have an answer to why it matters that the cardboard in your toilet paper is tested, other than some consistency and everything else. But yeah. And that brings us to the Grind My Gears segment on Family Guy. If anybody knows, a silly cartoon created by Seth MacFarlane. But what I liked is someone sent me this one time, because Morehouse does both force and torque. And it says when the tensile strength of toilet paper is lower than the torque required to enroll it. And those that get this joke can have a laugh on that. So I talked about takeoff and landing of an aircraft. And why is it important to get those measurements right? It's typically a weighing application. Sometimes it's a force application that's converted to mass. I would like it to stay in force, because force is force anywhere in the world, and we can get to that where mass requires in-place calibrations of the scales, and gravity can impact things and everything else. But so why is it important, right? what happens if we don't if the center of gravity is not correct in a plane? It wobbles. You have problems takeoff and landing, and you may even crash. So getting that weight and getting that aircraft balance is almost essential for our safety. And I certainly would want people to be doing that correctly. And we'll talk about truck and aircraft scale calibration a little bit in there. The this machine to the far left is a machine that can facilitate truck and aircraft scale calibration. So let's understand, talking about toilet paper and everything else, let's understand how all this works, because the end goal is to make us all safe and to make sure everything's tested, right? Tested properly. So what happens? How does force work? Well, we have the SI units of length, mass, and time, right? That's over here. So we're going to derive somehow from traceable to SI through a National Metrology Institute, recognized under the CIPM MRA. In our country, the U.S., I know some people from overseas, you likely have your own National Metrology Institute. England has NPL, which is the National Physical Laboratory. India has NPO India, England has NPO UK, Germany has PTB, Mexico has a CNOM, and so on. There's so many of them that goes on. But NIST, typically we follow NIST. They have great guidance online, and metrological traceability requires the establishment of an unbroken chain of calibrations to specific reference standards, typically national or international standards, in particular realizations of the measurement units of the International System of Units. NIST assures traceability to SI. The next tier is the primary reference laboratory like Morehouse. As I said, we're trying to have the lowest uncertainties so we can pass more instruments, because it's nice when you can say, hey, your load cell is good. You don't have to worry about recalls. You don't have to worry about all this other stuff that comes when you have an out of tolerance condition. And it's also nice to supply instrumentation with really low uncertainties. Our typical customer base then is an accredited calibration supplier. This would be someone that uses a calibration machine, whether it's Morehouse or some other manufacturer's machine, or maybe they may even made their own machine. They're buying standards and having us calibrated by primary standards. The reason they're not going to NIST is likely that NIST is 4 times the cost, because we both have dead weight standards. There is a penalty in not going to NIST though, and that penalty is our uncertainties are derived from, most of them on our weights are derived from NIST, and therefore we can not be better than NIST, and NIST does multiple measurements and really beats their numbers down. So NIST is at 4 to 5 parts per million for one standard deviation, where we're at about 8 to 12 parts per million. So then we calibrate equipment for an accredited calibration supplier. Guess what? They cannot have lower uncertainties than us. So they do their calibrations. Typically, they're most people that we work with in general that are in the accredited cal supplier that buy Morehouse machines are like 02 to 04, somewhere in there, depending on what they have, automated, not automated, a long list of things. And then they'll typically, or we'll calibrate working standards, dynamometers, force gauges, all the other stuff. And then the end result of all this is somebody goes out and calibrates those testing machines, and those testing machines are then used to, guess what? Test the concrete, test the rebar, test the fabric, test all kinds of different scenarios, test your keyboard, all of that. So what we want to take away from this is that measurement uncertainty data is cumulative from one level to the other. You have that unbroken chain of calibrations, each contributes to the measurement uncertainty. The tiers, tier 1 primary standards, tier 2 secondary standards, tier 3 working standards, and then the test machines. So I have some wrap up slides on here, and they are generally for people to as a visual aid. So talk about tier 1. That's typically what we're getting. This is a machine we provide. It's a 1,000-pound deadweight machine. We've made deadweight machines up to 120,000 pounds of force, and we can make them even higher. We can 500 kilonewtons, no problem. If somebody wanted 1,000 kilonewtons, no problem. They do get very expensive very fast. Now, NIST has a 4.4 meganewton or million-pound deadweight machine, and this is just a sample of it. So we calibrate the load cell in our deadweight machine. The next tier is somebody, hopefully our customer then buys a cal machine or PCM, and they calibrate. That calibrated load cell, this one with the red label, is then used as their reference standard to calibrate other load cells. And this is where they're typically getting the O2 to O4. And we'll go over that and how you do uncertainty. I have links to all this stuff. Hopefully we can simplify it if you're on here. I really want the takeaways to you to figure out, hey, I can use that spreadsheet Henry was talking about. I can do this, that. A lot of things we have done that we give away to try to make it easier for you to make the measurements, do your uncertainty calibrations and everything else the best you possibly can. So the types of equipment we have that we'll go over, you may or may not have seen these. I go pretty quick on them, and it's just an overview of what you may see walk into your lab or what you may own. And there's some tips and tricks along the way. Typically, we do not see that many people that know bolt testers. I've probably talked to classes, probably thousands of people have seen some type of variation of what we're talking about today from the early days. I've been doing force classes for 15 years and a ton of webinars. So it's at least probably 10,000 or more. But in that experience, not many say, hey, yeah, we do bolt testers. If you do them, great. If not, they're used to test high strength bolts. They basically take bolts, apply forces to the bolts, and do their testing. Calibration, for those that want to do it, this is a Skidmore Wilhelm bolt tester. And the note on this is that calibration requires special fixtures based on factory recommendations. Basically, you're a cal lab, you want to calibrate this stuff, you're going to need to work with the manufacturer to get the fixturing that they recommend for their calibration. Failure to do so can result in breaking their bolt tester that a customer sends in, and they are not cheap. Failure can result in improper measurements, which then that's not good for your customer, obviously. And they're pretty crude instruments overall. The accuracy is typically 1% of applied reading, and they work between 20 and 80% of the range. And they're typically used to, like I said, the structural fasteners and test torque tension relationships. And not many people see them. Probably not many people see proving rings anymore. We used to see a lot more of them because we didn't have all these load cells back in the 1920s, 30s, 40s, 50s. And the proving ring it's been around. It's a great instrument. It's proven that properly manufactured, they could last forever. If we had a solar flare tomorrow that wiped out the grid, we could go back and use proving rings. I don't know how many people would want to. They're not as easy to use as load cells for sure, but they last, and they are a really good check standard for your system. So if anybody's out there that has old proving rings, like I want to sell them on eBay, or do this, do that, I would encourage you not to do that. I would kind of keep one in a box as a check standard, because if someone knows how to use it and your system's like things aren't looking right, pulling this ring out does have benefit, more benefit than the 150, $200 that you may get on eBay for some of them if you go on there today. But yeah, they're not sensitive. I hate using the word not sensitive, but they're not as sensitive to rotational and positioning problems, the old analog ones. And basically it's because of the bending moment of the proving ring. It doesn't really vary much, which is significant in the region of the horizontal diameter, which basically leads to a nearly uniform strain distribution. Now the old ones had that dial and you had to be on top of it. You have to really see you have to see well to read them. And hence you can see the picture, it's like the pinup picture in the background of the old style proving rings. This is a digital proving ring. And if you have one of those old style rings that you're currently using and it's taking time and you want to upgrade it, we have digital upgrades, which means you take that old ring, we convert it to digital. Now you have a display that comes with it, and your speed and the uncertainty, a big component of uncertainty, that reproducibility, how well it repeats when positioned, and take it in and out of the machine, all that improves by about a factor of a third with many of the digital ones. So as well as your cycle time, and time is money. So it's a great upgrade if you have it. If you're thinking about replacing with load cells, we'll talk about load cells later so you can make the right decision. Other devices that we see a lot of are force gauges. They're typically used for calibration of certain testing machines, weighing devices, assembly presses, control instruments, cable tension, soil testing, you name it. I mean, if you just want to, you can use these as checking your luggage. If anybody's ever seen the pick up your luggage to make sure it's under the requirement, I think it's 50 pounds or about 25 kilograms, depending where you are, it might be 20. Uh, it's an instrument to use that to make sure your luggage isn't overweight. So these gauges, they can be analog or digital. Accuracies are all over the place, 0.1% to 2% of full scale. These handheld ones, interesting. They can be used for almost anything. I've seen them used in rubber applications, just seen them used everywhere. What I don't like about the ones in the middle is the fact that no one standardized anything. So we have this great setup with the PCM. Instead of standardizing a hole pattern to mount these gauges from like Shimpo, who are the Shimco, Chatilian, lots of other MSI, I think has some. Anyway, they're all different. Like each manufacturer, each engineer designs something just a little bit different, and different in two ways. Even the centering distance, which when I talk about centering distance, I'm saying this is your L bracket here, my crude drawing. Centering distance is, if this is my center hole, centering distance is basically the distance from the back of that bracket to the center of the hole. And they didn't standardize that either. So we have something, this is a part of our kit. We have something like 5 back plates and 15 of these other adapters. This is what we've come up with to calibrate them. If you calibrate them, the PCM can do tension compression. The technician can turn the wheel clockwise to go to facilitate the calibration in compression, and counterclockwise for tension. They can do them rather quick. It's a lot safer than using weights. It's a lot safer than other methods that I've seen people use. Brunel calibrators, we talked about these earlier. Calibrating in accordance with E74 is a limited load device or a specific force device. It's typically and then these instruments are used to check the downward force of the Brunel machines, and it's involves impressing a 10 millimeter diameter steel or tungsten carbide with a loading of anywhere from 67.5 to 3,000 kilograms into the steel surface. And then the hardness of that steel is determined by how big that indentation is. And there's lots of people making different sheets and stuff. ASTM E10, I believe is your standard there. E18 or E10, I often confuse those, but they reference E74 back. Traction dynamometers, typically used for adjusting tension or guy wire, field testing chain, rope wire, anything requiring precision. I don't know if I consider this precision or not, though the accuracy is typically 0.5% of full scale, and it's difficult to achieve on some models. The adjustment, those that do them, there's some tips. If you're close, you can move this face a little bit. You might get like 0.1, 0.2 divisions. So if it's on the verge of tolerance or not, otherwise it's very mechanical. You're taking off screws and unbolting and adjusting, and that's it. It's a pain. I can't say more than I've spent hours and hours on the same device trying to get intolerance, and then you walk away, go to lunch, and you come back and you do it again, and it can be and magically it's intolerance. So that's only because you warmed it up so much and it needed time to cool down. Lots of other things. Tension links, a lot easier to use. These come with problems though, and this is a big deal. This is one of the major notes for anybody that is in attendance today is the pin size of what you put in to fixture the calibration of these devices is extremely important. And when we look at proper pin versus improper pin is on the left. It's out of tolerance severely. This is a 0.1% device where we're showing 860 pounds of difference, pound force of difference just by varying the pin size. And it gets worse. Um, Here's a customer pin, and here's a 55,000, 25,000 KGF, 55,000 LBF pin. And these pins are marked Q1, Q2, Q3. So if the pins start wearing, just the difference in diameter of pins can cause these instruments to be out of tolerance. So we got into a habit of marking the pin top with an arrow. So we basically say, oh, here's pin A, and then you draw an arrow up. Here's pin B, you draw an arrow down. So people can orient the pin and at least get the same wear pattern on the result. Truthfully, these instruments are overspec, meaning that they really should, the specification on them really should, on this device, really should be plus or minus 100 pounds and not plus or minus 50. They should be a 0.2% device. And the reason I say that is because if you look at the difference in pins measured, 2.003 to 2.006, that's the min and max diameter on pin B, and pin A, those are some pretty decent tolerances overall, depending what you're measuring, what field you're in. Though out of 24 tests, just by rotating the pins around, 13 did not meet spec. So when you have that type of issue, just rotating pins, not even the size of the pin, it's telling me that the instrument is probably overspec'd, and the fact that, or underspec'd, I guess, and the fact that the specification or tolerance or accuracy of the device needs to be raised instead of 0.1 to 0.2. There's a cartoon on pins. You ready to calibrate? It affects. So quick change adapter system, what we came up with for our universal calibrating machines is basically you have this tension spherical system to calibrate these. You have tension member adapters, and then you have a clevis set. And why this is called quick change, this lean principles, is basically because we try to change this piece, only the pin size, pins, rollers. You can see smaller pin with a larger roller, so people don't have to purchase a lot of clevises. Clevises are very expensive. They're expensive to make. They're expensive to heat treat. Things can go wrong, such as warping and everything else. And therefore, by limiting that expense and just changing out the rollers, we developed a patented system for calibrating these tension links. And when I talk in more detail, there's the manufacturer's specification that's blown up. What happens here is you have this pin size, and it's called out and the E shackle pin diameter. And this is what you want to pay attention to on both of these tension links. Manufacturer absolutely is giving you this information and saying a 50-ton EDX needs a 2.75 inch pin. It is saying a 25 ton needs a 1.97 inch pin. It is saying a 20 ton needs a 2-inch pin. And yes, there is a difference between a 2-inch pin and a 1.97 inch pin. And that is why I showed that other slide with the min max diameter. You can call something out of tolerance very easily by using just a hair smaller pin, which is 50 millimeters instead of 2 inches. It is downright pretty silly to me. If it was spec'd higher, then it may not go out. But remember the original example here. And that original example was comparing a 2-inch pin versus a 1.75 inch pin with a 0.1%. And we were 17.2 times the specification just by using a pin that was a smaller diameter, smaller by about a 1/4 inch. If you're buying or want to buy something, I would highly recommend the crane scales. I like MSI crane scales. Challenger has some. These are very repeatable. The MSI ones specifically will hold. Ilon also makes some different crane scales and stuff. But in any case, the reason these aren't purchased as much is because they're super big and heavy. They do hold their calibrations. They hardly have any problems as far as I can put it in the machine. I can vary some adapters. As long as I'm pulling everything straight on that axle line, I'm good. These devices, accuracy is 0.1% of applied plus or minus 1 count. Those are the ones I like a lot to get that extra 1 count. There's different models. And then some manufacturers, the 1% of full scale. Like I said, they're just super heavy compared to the tension link. Other things you might not know if you're running a Cal Lab is if something comes in with batteries that are fresh versus old, if something comes in with rechargeable batteries, how many of you take the time to charge them to, their full limit? We got into the habit a long time ago of basically we're going to charge it with the batteries that come with it, and lots of instruments will operate okay with lesser charged batteries. We don't know. I don't have the list of instruments that do or do not. So we've taken the attitude of we're concerned with most. And since we're regarded to be the best, we're always going to replace the batteries if the batteries need replaced. The reason why is one of sheer laziness that we discovered. Though we were calibrating this older instrument right here to the left, and customer sent it in, batteries were pretty much working, though when we measured them, their charge was a lot less than a new one. And we didn't have the adjustment procedure. We said, this is out of tolerance. We need to adjust it. And one of the techs said, I don't know where it is. I'm just gonna put new batteries in it. And then when they put the new batteries in it, it was read 200 pounds high at 25 or 250,000. So by dumb luck of not finding an adjustment procedure eons ago, we basically changed our policy and procedure. And you bet the difference is we would have called something out of tolerance, a difference of 700 pounds at capacity, 0.28% on a device with a specification of 250. Now, should we have called it out of tolerance because that's how it was set in? That's where procedures and everything else come into play. And we're not going to measure the voltage of each battery and probably report that and then do all the tests associated with it. And I don't think people want to pay us to do that. So the policy is basically to put in new batteries. We start talking more, covered some basic instruments, and then we get into load cells, which I assume is what most people are calibrating right now. And what is a load cell? It's a force sensor that receives a voltage from an excitation source, hopefully a regulated power source. You can get in trouble if you don't have that. Digital indicator signal condition, and sends back a low voltage signal when force is applied. It's basically a transducer, converts one type of energy into another. We're going to read that and what it's doing. And when we read the load cell, the signal is converted by this principle. When there's no load on the cell, the two signal lines are at equal voltage. Of course, they're balanced, and when you're gauging and doing everything else, you're balancing zeros and all the other stuff. But you're balancing them so they're at equal voltage. As load is applied to the load cell, the voltage on one signal line increases very slightly, and the voltage on the other signal line decreases very slightly. So when we apply that force, all we're doing is measuring the difference between the two signals, and that's read by an indicator. Of course, that's assuming we have an excitation source and we're not measuring in current, and there's some other, uh, not to get too involved, but there are some other technologies that are out there. But generally, pushing on something, there's strain gauges there, we're measuring the change of those voltages. If you have a load cell, it's easy to do. It can be demonstrated by netting the meter. You put tare on the meter, push 0 on the meter, push on it, pull on it, and then you start reading change in output. What most people that have been through the course before haven't seen, we do have a webinar on this, is this. I added this section and I go quick on it, and I'm going to go that intentionally because we have a handout in your handouts, or if you go to mhforce.com under documents and tools, you can pull down our specification guidance that explains everything about that. But it's understanding load cell specification. And a lot of people, I do not think, understands what this stuff really means. And it is, if you're entry level, I didn't poll everyone when we started, but if you're entry level, if you're advanced or whatever, I can poll as we go to break and let you answer that to figure out where we are. Though this stuff it's kind of overwhelming, and people are chasing things that may or may not be the right thing to chase. So static error band, this is a hard definition. It's hard to explain. It represents a subset of errors in the load cell's output. It includes sources such as nonlinearity, hysteresis, and return to 0 after loading. A lower SEB is a good thing. It means higher accuracy. For example, the static error band for smaller capacity load cell is 0.02 of rated output, meaning the error is within 0.02 of rated output. Though the math behind it and what we do, some people are talk about all this other stuff, terminal point. It gets beyond the scope of this, and we could talk about this topic and static error band for an hour, and we've talked about it internally for hours and hours, and what's the best approach, what best represents what people need and want. And we kind of aligned a lot with industry on this because we're using the same formula that others such as Interface, Tovi, I think HBM are using this formula for static error band. Other manufacturers use different ways to calculate it, which may or may not be the right way depending on your thoughts on the process. So basically we're saying, hey, we're going to take this line and we're going to draw it, and we're going to account for ascending, increasing, and decreasing forces, and the variability from that center distance is going to be less than 0.02%. So if this is my center line right here, I'll try to draw it red right here, we're basically saying to the top or to the bottom is 0.02. You could have an 0.02, that could mean 0.04%, and that's when you get into linearity, nonlinear. So somebody would say, well, static error band's 0.02, but nonlinearity is 0.2, though hysteresis is 0.3, and you say, okay, that's okay overall because of what we're measuring. We're measuring and how we're plotting it. So nonlinearity, this refers to a deviation from a straight line. This is what people tend to look at the most from my experience, and that A lower value indicates the load cell's response is more linear, which is ideal for precision measurements. Maybe, maybe not. Indicators today are really good, and we'll talk about indicators and how to choose the right run. Um, and reported nonlinearity can vary from the state of load cell depending on how this straight line is defined. Typical definitions are endpoint, best fit line through zero, all kinds of things. This is why in our guidance that is attached in the handouts that we say, this is what we do. Here's our formula right here. You want to match? You want to see how we calculate nonlinearity? That's how we do it. And it's expressed as a percentage of full scale. So you have your linear response, and then you have what the actual, in red, what the load cell is actually doing. And then hysteresis is the descending curve, and it measures the difference in output between the ascending and descending values. It reflects the load cell's ability to return to its initial state. Lower hysteresis values, low as O2, less error, better accuracy. So 0.02% basically says I have an ascending curve and I have a descending curve. And the difference, the maximum difference between these, it looks like on this drawing here, is 0.02%. So my ascending value is going to be very similar, is not going to differ by more than 0.02% from my descending value. And that's how it's calculated. Do you need it? Do you use the load cell making descending measurements? There's important pieces here that your descending curve, this top curve varies depending on, if I only go to 50% of capacity, the curve looks like this. That's a little beyond this. Non-repeatability is the maximum difference between repeated measurements under the same conditions. I wish this was on every spec sheet for every load cell because it tells you a lot, and it's under the same conditions. If I apply a force to the device, one run, and I record the output of the load cell, and then I apply the force again a second time, record the output of the load cell, and then I apply it again a third time, maybe a fourth time, and report the output of the load cell. I basically, difference between 1 and 2% of full scale, I'm basically just saying, hey, what's the difference between run 1 and 2? What's the difference between 1 and 3? What's the difference between 2 and 3? So, and I'm plotting all these, the matrix of all of these, and then we come out and say, all right, I did this many runs, and the worst case is 0.03. That doesn't tell me how well that load cell is going to perform when I put it in another machine. As far as the output, it's basically telling me that if I have a good machine and I apply the same force without rotating it 3 times, that I should expect that non-repeatability. I should expect the load cell to repeat within 0.013%. Different thing, different temperatures, there's lots of other stuff that go into this. Creep, when you're doing an uncertainty analysis. Creep, not the song by Radiohead. Again, bad joke. But this is a really good specification to look at. And creep is the change in load cell signal occurring with time under load with all environmental conditions remaining constant. And then you have creep recovery, which is the change in load cell signal occurring with time immediately after removal of load, which have been applied for a specified time interval, environmental conditions and other variables remaining constant. So this VL, this line is creep under load. So I apply 10 meganewtons. We're going to go for the gusto on our maximum capacity. I apply 10 meganewtons and I hold it. And then what we do is we monitor this load cell's performance and report it. That's creep. Creep recovery is at some specified time interval, maybe at 60 seconds after removal of the force, I start plotting the creep recovery for 5 minutes. And I record the maximum result. These are typically specified in 20 minutes, though most standards do not make us wait 20 minutes. Another specification, off-center load sensitivity. It refers to how much the load cell's output changing when load is applied, off-center, not directly along the central axis. Basically, that just means, hey, what happens if I don't get things perfectly straight? So specification from the data sheet specified 0.1 per inch. This means that if the load is applied 1 inch away from the center of the load cell, the out could deviate by 0.1% of the rated output. That is a very low number. Some cells, which we'll look at later, have tremendously high numbers there, and people do not pay attention to them, or the manufacturer does not report them. Side load sensitivity, how much the load cell's output changes when a force is applied perpendicular or laterally rather than along the attended load axis. So there's a picture of what that means, and can introduce measurement errors causing strain or parts of the load cell to measure force and directions. Typically, if your machine is not level, if I have a nice, and I'll try to dry this, if I have a nice level machine versus a machine that's not level, and I sit my load cell, poor drawings, on this, I'm going to have much worse results than if I sit it on a flat surface. So um, again, could deviate under the maximum load, and more on that is in that specification sheet. Other piece, zero balance, refers to the output signal of the load cell when no load is applied. Ideally, the load cell should be trimmed and should be zero when no force is acting on them. Due to manufacturing, due to whatnot or ever, everyone's almost different. If you could measure 10 decimal places, probably every load cell is going to be different with your zero balance, right? It's how far out do you go? Eventually, you cannot, every thing has a tolerance for a reason. Um, anyway, so imbalances in strain gauge, there is usually small non-zero output when the load is at zero, and that small output is referred to as zero balance. What's nice about this is we take this on lots of our measurements. This is a nice reference point to see if something's happened to your load cell. If it's been overloaded, misused, or anything else, you can track your zero balance. The typical specification is for at least our load cells is for specification is 04 millivolts. So 4 millivolt cell 04, a 2 millivolt cell 02. If it's higher than that, something's happened to the load cell. Other specifications, range compensated, where's it designed to be used within the specifications. And then operating, well, you can go to 15 degrees F, but here is broader compensated range, but the load cell is going to function, but it's going to experience a lot more temperature related errors. And then the sensitivity effect per 100 degree F, that assumes it within that compensated range, and how much it changes with 1 degree of temperature. So the lower that number is, the better for you, especially if you're not holding your temperature to the same as the lab that performed the calibration. And then there's the zero effect, that also zero changes with temperature as well. All Morehouse load cells are designed with temperature compensation to minimize errors caused by these temperature fluctuations. And if you're not temperature compensated, you can have rather large errors. Input output resistance, more information. You have the PDF, you can look at this. It's electrical characteristics, useful in troubleshooting. If it's 350 ohms and all of a sudden it's different, then maybe something happened. Sensitivity referred to as full scale, normal output signals, insulation resistance, all of these specifications are there. Many load cells are designed with Wheatstone bridge. That's pretty easy. That's how things are gauged. Input resistance is a resistance measured between the two excitation terminals, positive excitation, negative excitation. On Morehouse load cells, that is pin A and D, and then output resistance is your signal, and on Morehouse load cells, that is B and C. On the Shearweb load cells, those should be about 350 ohms. More information is on that. I wanted to make sure we talked about everything. Now here's safe overload. This is one you want to pay attention to a lot. which means how much force can I put on it before the device fails or before we exceed the limit and damage the load cell. Most of our load cells can handle 150%. We do have some very specialized small compact compression cells that only do 110% because of their design. However, most do 150%. I don't have any pictures of those. They're super special. And then weight and material. How heavy is it, right? If I'm going to carry something around, I want to know how heavy that thing is, because I'm going to ask somebody, am I going to ask somebody to lift a 117-pound load cell? Probably not. I'm probably going to need equipment, specialized equipment, maybe cranes, other things. So safe overload, typically 120 to 150%. Ultimate overload, this is a part of failure where you actually pull the load cell apart, which is no bueno, no good for anybody involved. It's actually dangerous. If you're in a testing machine, it's probably safer than if you're. It's a lot safer than if you're in a cow machine. But if a sensor's rated to 20 kilonewton, safe overload's 150%. Ultimate overload's at 200%. So you have your rated capacity range. Safe overload. Oh, my technician might have overshot a point in a UCM. Don't worry about that, right? They can, unless they've overshot the point by, if they have 100,000 UCM, unless they've overshot the point to 150, load cell's still good. And then ultimate load cell, if they've gone to 200,000, the machine's probably coming apart with some other things. Additional specifications that many may not tell you is things we do, like, hey, how good is this if we rotate it, if we do all this other stuff in here? And that's the ASTM lower limit factor. If you know anything about the ASTM lower limit factor, great. If you do not, we will talk about it later. So I'm trying to get my. So, and some of these links, the sheets that we have here, oh good, I have some questions coming in. I do see them and I will answer them. Some of these, there we go. So switching out of the PowerPoint, death by PowerPoint slide deck to our documentation and tools section. All kinds of stuff here. Here's our uncertainty calculator, easy to use. Load cell selection guide, which it'll probably open digital. Maybe I cannot. I'm not a big fan of good. I'm not a big fan of the web version of Word. But so what this tells me is, hey, how good do I want this load cell? How good could I expect this load cell to be? And just made this tool that says, hey, I need a 50,000-pound load cell. And it says, hey, the ultra cells, ASTM, we're going to guarantee a 0.05% of full scale. Well, how good is that on the ultra? Well, that means my loading range and the percent of capacity number, which is different. When we say 0.05%, people get all excited and say, oh, my load cell's 0.05%. Oh, no, the wording in there is 0.05% of full scale. So what does that mean? Well, that means 0.05% of full scale translates to 0.01% at half scale, 25,000, and at 1,000 it translates to a 0.25%. So this guide, it's super easy math. It just goes through and said, all right, well, if I bought a precision cell 0.1 at full scale, well, guess what? At half I'm 0.2. And if I want to go out and do E4 calibrations, it's like I'm going to have an ASTM Class A verified range of forces from 2,000 pounds to 50,000. If you know ASTM and you know what you're seeking and you're in that market, this probably makes a lot of sense to you. If you do not know ASTM, we'll talk about it later. Probably doesn't make as much sense to you. The way you can go about this is just to say, look, 005 means this, right? It means that at 10%, I'm typically going to be at 0.5 or better. And depending what I want to maintain, if I'm using test accuracy ratios, which I do not recommend, using that, that would mean that if I wanted a 4-to-1 on a 0.1%, that I could use, I may have to buy the ultra cell, because that's going to give me, if I'm calibrating devices to 0.1%, that's going to give me a range of my 4-to-1 is going to be met at 10,000. But we'll talk about all that other stuff in a bit. So we also have the guidance there, as I said, that's online. It covers more. That guidance document also has the Excel code, so you can just copy and paste if you want to play with Excel. We have it for SEB because it's a little complicated for that. Now, we have some static versus dynamic forces to end with. When I'm talking about most of these conditions, I'm talking about static loading, which is the load is applied incrementally and held. Basically, we apply a dead weight to the force instrument, and we say what that device reads at 10,000, right? Time, once stabilization has occurred, we typically take multiple readings, average those readings. It takes us about we hold force for about 30 seconds. Dynamic is the load changes continuously. No stabilization time, making precision measurements more challenging due to system inertia, response times. You're into frequencies, you're into sweeps, you're into all kinds of other stuff. And if you think about testing a machine, breaking a specimen, it's going to go, and all of a sudden it's going to break. So the load on that thing is constantly changing. Measurement uncertainty is different between static and dynamic. Right now, everything traces back to static. We're disseminating from the kilogram to NIST dead weight machines or NMI's dead weight machines. Eventually, I think there'll be some dynamic standards, part of an ISO committee that's working on them, but it's going to be a bit.